you can see the distance in here, pretty much the height of the the display in here will be the distance between the observations, or the clusters and the observations and the clusters altogether. So so this is an example in here where we have simulated data, 45 observations. From the plot in here, we can see that maybe we will end up with 3 clusters. So when you build, when you use hierarchical clustering method and you display the tree, it will, you can see like at the beginning, it will, group observations one by one into smaller groups, and it will go bigger and bigger, and then we'll display everything. So if you choose a cutoff at distance 8, for example, so that's the distance in here, you will end up with 2 groups. But maybe, because of, we have the figures that we can see, maybe it's better to make a cut at, around 4.5, around this distance in here, by which we will have 1, 2, and 3 groups or clusters. So this is pretty much what we discussed last time. The choice of the linkage in here, the choice of how you calculate the distance between 2 clusters. So we can choose, between those different linkage types. The most common used one, the average, where you pretty much calculate all the distances between all the points in each cluster, and you take the average. So we talked about this last time. Now, for the similarity or dissimilarity measure, we used Euclidean distance, but in some cases, you may consider correlation. So in this example in here, it's a better choice to use correlation between these observations rather than the distance. That's pretty much when you have a problem where, like a time series. So in here we see like the difference or the variation in the observations across time. So we have different time points, and in this kind of problem, it's better to use a correlation-based distance rather than Euclidean distance. And the example at the end, I want you to go through this example. So there's the slides in here and also in the book, in the textbook, and you can access the data set from the library that comes with a textbook for clustering cancer patients using gene expression data. And the clustering that we end up with pretty much can determine the types or the subtypes of cancer among the cancer patients that we're studying in here. So, and then there's also the reference paper if you need to go and get more details. So the algorithm we use in this clustering, or the algorithm used in this paper, this research paper, is a hierarchical clustering. The linkage type was average, and the correlation was used as the dissimilarity metric. It was more appropriate to use the correlation rather than the Euclidean distance. So all the details that you can find in this study in here, in this research paper, using clustering, and you can look at the results that the authors of the paper show in here, where pretty much, so this is the clustering tree, and based on domain knowledge, based on experts in cancer types, they were able to identify for each cluster, or then they were able to label each cluster. So these are the names given to each cluster based on domain knowledge, or based on attributes that those observations share in one cluster or one group. So so that's the study, and in a way it will show how clustering can be used in in this type of studies. This is like one of the, it's a 2003, so it's an old research paper. So it was like among the first application of clustering in genomics to do clustering. But nowadays, I mean, we have a lot of more advanced algorithms in clustering, and the applications of in different areas rather than just in genomics. The last thing, practical issues about clustering. You need to scale the variables. That's very important. Before you apply any clustering algorithm, all of your variables, they need to be on the same scale. Now, issues for hierarchical clustering is pretty much, the dissimilarity measure. What should you use? Euclidean distance will work in most cases, but if you have data with like a temporal that has a temporal component in it, then maybe you need to consider a correlation. The type of linkage, most people will use average. That's kind of the practice in doing that, the common use. But you can try the different linkage types, and you can do cross-validation, for example, so you can think of it as a tuning parameter, the linkage type, and choose the one that will give you the best results or the best cross-validated results. Choosing the cluster, how many clusters. So in k-means, you need to specify this beforehand, which is problematic on its, on its own. What's the best value for k, or how to choose k. And even in hierarchical clustering, we don't need to specify this at the beginning, but we need to specify this at the end. But the graphical display of the clustering tree will help us in making this decision. So there is a way to overcome this difficulty when you use hierarchical clustering. And finally, choosing the features for your clustering. You can basically do feature selection before you apply your clustering algorithm. So that's pretty much the conclusions for this chapter. For unsupervised learning, it's a big class of problems in machine learning, and and clustering is kind of one of the topics underneath unsupervised learning. There is the difficulty in unsupervised learning in comparison to supervised learning is in how you evaluate, because there is no gold standard, because we don't have an outcome variable, and sometimes it's difficult. There is no like testing accuracy by which you can report and by which you can tell how good your method is. But anyway, it's still an active field of research, and maybe you will learn more if you are considering machine learning in practice. You will learn more about unsupervised learning, other methods in clustering, and also using it for visualization and encoding. So that's it for the topics of our course. And before we start with the presentations for the students project, let me see if you guys have any questions. So already we have some questions. No, it's the hierarchical tree building algorithm is different than the tree-based methods. Sure. And also remember the code. The R code is also posted on Canvas, so you can look at how you can do clustering in R. So although we don't have an assignment for this chapter, it's there for you and for your, to use as a reference for you, if you will, if you are ever to use k-means or hierarchical clustering in your research. All right, so no more questions, then we can start with project presentations. Jose Miguel?
Sure, thank you.
Okay, sure.
Hey guys, I hope everyone's doing well. And so just to talk about the project presentations, how this will go down, is that we're doing 3 presentations today. The first one is by group 1, with Lucy, Tara, Allison, Newport, and Frank. Then by group 9, Wen, Hao, Chin, and Kaha. And then by group 2, Fan, Sanjeev, Shivani, Tanya, and Kush. Okay, now the talk will be split up into a background method section is the first person. The second person is the results section, and the third is the discussion section. And for during the presentations, all the students should pay special attention to each presentation, and particular to the criteria that you will score it, because your score of your peers is you will input into Canvas, and you're going to use that as a in order to assign a portion of their score. Now, if you go into Canvas and you look under, for example, quizzes, you'll see a for April 13th, Group 1 has the names of the students in that group, and it has an evaluation form for the final project presentation. And if you click on that, let me see if I can share my screen here. Okay, can you see my screen right now? By the way, I'm not looking at the, okay, so here is a screen, and I'm going to click on this first group so you can see, and then you would fill that out. I'm going to preview this so you can see what the questions are, so you keep these in mind. Now, you have to submit this for every other project, every other group, but you do not fill this out for your own group. Okay, so don't evaluate. Your self-evaluation is the within groups evaluation is in a separate area. Okay, so this is only for groups that you are assessing that is outside of your own group. And so here you can see that if the student does not submit the form, that student's final project grade will be deducted by 3 points for each group they miss. And so it's important that you are there to assess each of the groups. And so the questions are, was the research question and main hypothesis clearly defined? From an A to D, was a chosen statistical method appropriate to the problem? Appropriate to the problem? Were the results clearly presented? And an overall evaluation from 0 to 10, where 0 is the worst score, 10 is the best score. Okay. And then any comments that you want to leave for that group, and then we can pass those comments on to those groups as some constructive criticism. Okay, so are there any questions about that aspect? Okay, so here, again, we're splitting up the 3 sections there. And J1, if you can time each of the groups, so you have 10 minutes for the presentation, and once the presentation is there, let's say once they have like 2 minutes left, you can type that into the into the chat. I accidentally muted myself. Okay. There we go. Okay. Any questions from there? I see, Jae-Hwan, that you responded. Great. Okay. So I'll and then so for group one, if you want to unmute yourselves and decide if you want to have one specific person that's going to drive the PowerPoint, then we can do that. Looks like Allison's going to do it.
Yeah, we've already worked out that.
Okay, perfect. So now what I'll do is I'm going to randomly select the person using my trusty random number generator on my phone.
And
So I'll tell you who's going to go first, second, and third.
oh,
Actually, I'm going to do this, I think, easier if I just do this. Let's open up R.
mm-hmm.
So the first group has 5 members, and so it's going to be 1, 3, and 2. So Lucy is first, and then Allison, and then Tara.
Okay. We did have one question. If for some reason we have connectivity issues, is it, or if a single person has connectivity issues, can somebody else in the group just step in?
That should be fine, yeah.
Okay.
Yeah.
We think we should be fine. We have people on backup phone, so.
Okay. If it looks a little suspicious because just then, like, they didn't know how to answer the problem, and then suddenly they have connection.
Okay. And when you ask questions at the end, will they be directed to a single person or anybody in the group can answer?
Yeah, at the end, anyone can answer.
Okay, perfect.
All right, let's go ahead and get started then. Jae-Hwan, if you want to start the timer.
Can you guys hear me?
Yes.
Okay, and me too?
Yeah.
Oops. Okay. All right. All right, ready? Okay. Hello, everyone. Today we will be presenting our project on predicting subarachnoid hemorrhage mortality. Next slide, please. Subarachnoid hemorrhage, also known as SAH, is a serious condition with high morbidity and mortality. Causes of this condition include cerebral aneurysms, congenital malformations, trauma, vasculitis, comorbidities such as diabetes and hypertension, and drug abuse, as well as others. Development of a robust algorithmic model to predict mortality is needed to improve patient treatment options, identify prognostic indicators, and decrease overall medical costs in the healthcare industry. The goal of this project is to develop a robust model that predicts mortality for SAH patients based on selected predictor variables. This model uses the Cerner HealthFax EMR dataset that collected data from over 700 hospitals in the U.S. between 2000 and 2015. We hope this presentation will be informative in helping understand and predict SAH mortality outcomes. Next slide. For both the original TRAIN and TEST dataset, the procedures and medications were cross-referenced with the patient demographics and then merged to form a clean TRAIN and clean TEST set. We inspected the summary statistics of patient characteristics stratified by outcome for the training dataset. The clean training set was divided into 5 training and corresponding test data subsets using a 75-25% split. We then fit preliminary models using these 5 training subsets and validated them based on their corresponding test subsets. The methods used included neural net, support vector machines, lasso, elastic net, random forest, and boosting. Cross-validation was used to find the best parameters for each of these models. We then found the misclassification errors by applying each of these preliminary models to the corresponding test subset. The average misclassification test error and area under the curve were considered in predicting the best prediction method. Finally, we applied the best selected method to the original clean test set to predict mortality outcomes. And of course, all analyses were conducted in our favorite language, R. Okay, the data sets were transformed into a wide format. We used binary recoding to denote whether a patient received each procedure or medication. A 0 indicates the patient did not receive, and a 1 indicates the patient did receive that procedure or medication. A new variable denoting duration of hospital stay was created based on the difference between admission and discharge times. No observations were dropped. However, due to sparsity within classes of race, multiple Asian race categories were grouped together, and biracial subtype was merged into the other subcategory. Patient ID, admission time, and discharge time were removed as they were not needed for model selection. Subsequently, we deleted all procedure and medication variables that did not overlap between the test and training data sets. Finally, the training set was split into the previously discussed subsets. Next presenter.
Next, we performed summary statistics on the training data set. These are the summary statistics of the training data set, stratified by death, defined as in-hospital death or discharge to hospice care. We found that there were significant differences between patients who survived and died based on age, race, length of hospital stay, number of procedures, and number of medications received. There was no significant difference in gender. We next fit our preliminary models and cross-validated them. This table describes the mean training error percentage, the test error percentage, the mean training AUC, and the mean test AUC produced by each attempted model. Cross-validation was used to pick the appropriate parameters for each model using the 5 training sets. The model with the best parameters was then run on the 5 test subsets. Boosting, lasso, elastic net, and random forest may have had lower test error rates because their inherent underlying algorithms included variable selection. We can also see that the mean training error is decreasing as mean test error is increasing. Neural net has a 0% mean training error, suggesting that it may have overtrained the data. The best performing methods were boosting based on mean test error and random forest based on mean test AUC. However, the mean test AUC for boosting and random forest were similar. Additionally, the low mean training error for random forest indicates it may have overtrained the data. Therefore, boosting was selected as the final prediction method. A final model was trained on the full trained data set, and predictions for death were made on the full test data set. Now we get to apply our best method, boosting, to the final test set to predict mortality. These are the final boosting model parameters. The table shows that the boosting training error was 12.56% and the area under the curve was 0.9008. The selected best model included 4,943 trees, 1,110 predictors, and 219 non-zero influence predictors. The graph plots the 5-fold cross-validation error versus the number of trees while tuning the boosting model. The green line is the test error and the black line is the training error. The blue vertical line shows the optimal number of trees that were chosen. The top 10 influential predictors are duration of hospital stay, age, intubation, use of norepinephrine, ondansetron, and radiography. You can see that ventilation is listed 4 times. These predictors have biological plausibility. Airway breathing and circulation are the most vital steps to ensure preservation of human life. Ventilation and intubation are key in maintaining patient survival when deemed necessary. Duration of stay has been previously documented as associated with morbidity and mortality. The medications included in this table are routinely used in patient treatment protocols for supportive care measures. We then applied our final model onto our clean data test set to predict mortality for each observation. An overall mortality rate of 31.72% was predicted using the boosting model as compared to the training set death count of 25.49%. Here we can see that patient characteristics of the clean test dataset stratified by the predicted mortality. There was a significant difference between the two groups in age, length of hospital stay, number of procedures received, and race. There was no difference between number of medications received and gender. The only difference compared to training dataset was that in the test summary statistics, the difference in number of medications between predicted outcomes was not statistically significant.
There are limitations to this model, however. As complexity of the classification increases, boosting can have increased costs with respect to both time and computation. As with any prediction method in a high-dimensional setting, boosting may overfit the data. Clinically, the model also applies to patients with non-traumatic SAH cases. It cannot be generalized to SAH cases due to other causes. Next, the originally collected training data may be geographically skewed because larger metropolitan hospitals may have higher SAH patient volumes than rural hospitals. Therefore, this model may not apply as well to those rural hospitals. And finally, this model may not be completely up to date with regard to procedures and medications. This is because 5 years have elapsed since the observations were collected. During these 5 years, new technology and medications may have been developed to treat SAH patients. In conclusion, why does this boosting model matter and why is it appropriate for these data? Boosting is a decision tree-based method that is optimal for aggregating and combining poor standalone predictors into combinations that are more efficacious and useful. Development of a robust algorithmic model that accurately predicts mortality outcomes for non-traumatic SAH cases is very beneficial to physicians and hospital systems in general. It can help physicians better identify procedures and medications for patients and determine the best treatment plans possible. It also allows physicians to give patients' loved ones a more accurate prediction of patient prognosis. Finally, the optimal procedures and medications to use for each patient may ultimately help save hospital costs, improve quality of care, and patient safety. And then we have references and questions. We're done.
All right, thank you.
Great.
Do you want to go first with our questions, or should we open it to?
Yeah, let's open that for the students.
Okay. All right.
Oh, should I keep that open? Sorry. Do you want to keep seeing our penguin?
Yeah, you can share the slides while we have take questions from students.
I have one question. Because we don't know the training, testing output, how do you guys calculate the testing AUC? Because we don't know what is the true.
Sorry. Sure. So what we did was we split our training set into 5 subsets. And so where you see our test and train AUC, you're seeing the test AUC for our subset. So it's not our true test set. That's like a sub-split of our training set.
Okay, got it. Thank you.
Sure.
Other questions?
Okay, I keep sharing the wrong screen. There we go.
Dong, go ahead and you can use your mic if you want.
Yeah. Did y'all use the cutoff in regards to the number of medications or procedures, or did you just include them all in your model?
We included the ones that we included the ones that overlapped. We included the ones that overlap between the training and test subsets only, the sets only. We tried to basically not exclude any of the observations or any of the variables as much as possible. Okay, go ahead, Tara.
But
that's what I was going to say.
Yeah, but as we mentioned, some of the methods use variable selection, so there was a reduction in the number of like medications and procedures that ended up included in our final model because of that like inherent process.
Okay. Cool. Thanks, y'all.
Other questions?
Can you hear me? I have a question.
Yeah, we can hear you.
Why did you choose to dichotomize the treatment variables? What was your thinking with that? Did you feel like you lost information and was it worth it?
The dichotomize which variables?
Like the treatments, instead of having them where they were like numbers, you have yes, they got it, no, they didn't get it.
I think maybe our MDs can answer that.
Sorry.
Oh, go ahead.
Oh no, I was just gonna say that, are you talking about like our, where we set our medications and procedures to ones and zeros?
Yeah, so essentially you're saying that someone who got epinephrine 3 times is the same as someone who got it once, because they're both just going to be a 1.
Oh, gotcha. Yeah, I think the MDs can answer that better.
We can put this to 2 MDs on our team.
Okay, so here's the thing. When you have a patient that comes into the hospital, that patient has a bunch of orders that will be standing in and written in every day for the patient. So depending on the length of stay, that patient will probably get norepinephrine every day. We'll get ventilation every day. We'll get this and that. These are just standing orders. They'll get normal saline every 8 hours, for example. So what's more important is duration of stay, because it takes into account both whether this person got the medication or not and for how long that person got that medication. So this was more basically medically accurate, actually, in a way. Tara, you want to add on?
Yeah. Oh, well,
that was our main thing, because the way you set up treatment plans is, you know, you're giving this every certain number of hours, or of course depending clinically on how the patient is doing. So yeah, we went with duration as being blah blah blah. What's the word for that?
Containing the information.
Taking that into consideration.
Yeah. Yeah, so for like the statisticians, basically the duration has all of that information that would have been contained in the number of times that each medication or treatment was received. So we decided that it made more sense to just keep the duration variable to get that information. Otherwise, we would have the same information included in multiple variables. So we thought we would get a better model and better prediction if we separated it.
Correct. Right on par.
Okay, thanks for your justification. Can I give a shout out to Caitlin and just say thank you for all the help you've given me all semester on the discussion? You're welcome. I needed to get that out before the end of the semester, so I thought that was great since you asked the question.
All right, great.
Thanks.
Okay. You do have another question? Maybe just I have a few questions, but if anyone else has a question, you can just type it into the chat. All right. So let's see. One thing that I'd like to mention is like this. So talking about the hospital length of stay, right? If you're trying to make a prediction at day 3 after the person comes into the hospital, you actually don't have that information about hospital length of stay. That's like looking to the future. I mean, I don't know if maybe one of you does fortune telling. Maybe so, like as a side gig. But if not, then you probably wouldn't have that information, and so it's kind of unfair to use that. You want to comment on that?
Sure. So what you can use is how long they've been in the hospital so far, right? So just like we do with survival analysis, like it's sort of like censoring.
Right, but the way that you defined hospital stay was the difference between the time of admission and time of discharge. Right.
So if you were going to use this for somebody, like if we're going to use this for somebody who's in, so you're saying like it's unfair to use it because somebody's in the hospital currently, right? So I think we were trying to see that. So I think that is another limitation of our model. I think what you can do is we could incorporate that later, but I think that is a limitation as far as applying this for people who are currently in the hospital.
Yeah, and so that's something that you should just keep in mind when you're kind of creating variables and thinking about. And honestly, you're not the only group that did this. There are several other groups that did this as well. You have to really think about, okay, if you're actually implementing something like this, and you get to the time point of when you're trying to make a decision, you want to use all the available information you have at that time point, right? And so to use information that's happening in the future, actually you can't do that. You wouldn't have that as an input into your model. And so you have to be careful how you do that. And actually there was another variable which I think it was put in there because of the way that the EHR data is set up. But there's a variable that you found to be important was the continuous invasive medical ventilation for 96 hours, 96 consecutive hours, more or less, right? And all of this data is actually supposed to be within the first 3 days of their hospitalization. And so, the first 3 days would be 72 hours, so you would actually know that it was 96 hours, had 96 hours hasn't passed yet, so you have to be, again, kind of looking into the future. So that's, again, kind of just a limitation of the way that the HR data is set up, but it's something that you should just keep in mind when designing these types of algorithms. Now, yeah, go ahead.
Sorry. Well, so clinically speaking, when you have patients who are in the hospital, so yeah, that limitation might be if you have like an incoming patient, but if you are on your day 3, you still can use the duration variable to say, hey, the longer these people are staying in the hospital, the less your prognosis gets. And so you can still use that variable as in like prognostic-wise to be like, hey, I now know this person has been here for this long. The longer we stay here, the more likely this is going to happen. And so if you're on day 3 or 4 or whatever, then you could start using that for your prognosis. So it might be limited on the first day, but as each day passes, your prognosis might get more accurate because of that. So I still think it's somewhat important to know.
I concur 100%.
Yeah, I'm not arguing that duration of time on invasive ventilation, mechanical ventilation is not important. I'm saying that specific variable, which splits it at 96 hours, is something that you wouldn't have that you shouldn't have in your data before 96 hours. And so if there were another way to just capture the number of hours of mechanical ventilation and use that would be the better approach to do this. And again, this is kind of just a limitation of the EHR data, the fact that that variable was still in the assigned to a time within the first 3 days. Now, I think that your methods for choosing the final model were very good. Your approach was good. You had a very nice discussion and introduction. And so in general, those are the main issues that I found. Dr. Yassin, do you have any other comments?
If you can go back to the beginning of your slides when you mentioned the split of the data between training and testing, you mentioned you did the split 5 random splits. What does it mean?
Yeah, so what we did is we took the training data set and we took that set and we repeated a 75-25% split. So we split that into 75% for a training set and 25% for a test set, and then we repeated that. So just like we did in our homework where we would be given like a set, we split that entire data set into 75 and 25% for training and test. So we did that with our entire training set that we had so that we could compare the different methods. Since we don't have the outcome for the test data set that we were provided, this way we could have a test AUC and a test error rate to do like our own cross-validation.
So when you take the 75% split, do you do cross-validation, and then you apply this to the leftover 25%?
Yeah.
Yes.
Okay.
Yeah, we use cross-validation there.
Yeah.
But then it's done 5 different times, so then we average the results each time to get one to be able to compare them. Is that what you're asking?
Yes. That's fine. You can do that. My other question is for the table where you showed the comparison. If you can go back to that table, the comparison of all different methods. Why neural net is doing so bad?
Yeah. So
Good this question.
we were wondering this too. So we have a couple of thoughts about that. I don't know if somebody else wants to talk about this other than me.
Well, we talked about the architecture of it. We only tried, 1 or 2 in layers. Because of the limitation on like our computers and stuff. So it could have been something that maybe tried different number of layers, and then the way we set up the nodes were in, I think it was like 50 at a time. So like 200, 250, and so.
I think it started at 500.
500, yeah. Okay. And then, so if you really had a nice, good supercomputer with a server or whatever, we probably could have explored neural net a little bit more. So we're thinking that might be part of one of the main reasons.
Okay, so you didn't try and tune the hyperparameters to get better results.
No, we did. We did try and tune the parameters, but I mean, the tuning of the neural net with the limited number of parameters we allowed it to tune took multiple hours. And so, and we just learned neural net at the end. And it wasn't in our book. So there just wasn't time for a computer to run and for us to get results from it.
Okay.
Yeah. So I'm going to throw that on you to see does you want our computers to actually tune more options for that to get better results for neural net.
Sure. I would, if I were you, I would remove a neural net from my table. I would
But
just
you
say,
did it, so
yeah, I would just say that I tried those methods, except so you don't need to mention the methods that that are failing in your experiment or that didn't show good results.
Okay.
Oh, because we didn't actually talk about the ones that we didn't consider.
Correct. So neural net should be one of them.
Okay.
Oh, gotcha.
So we should have just pretended like we didn't consider it.
Yes. Other than that, it's really good presentation and good job. Excellent job, actually.
Thanks.
Thank you.
Thank you.
Yeah. Actually, I had one last question about the random forest. Did you try to tune the number of variables to use at each split?
Yes, we did.
Okay, I didn't see that in your write-up.
Each tuning.
Yeah.
Can you show me the tuning that you did for that? Do you have a slide on that or not?
Oh, we didn't do a slide on on tuning for each individual model. We thought that would be too long. Yeah. We just have the final tuning on the model that we used.
Just for, do you mean for boosting our final model or for random forest?
For random forest.
Okay, no, we don't have a slide. We just mentioned that we did that.
Okay.
Just because within the models that we didn't end up selecting, we just mentioned that we do it.
Okay, all right.
And also so that we didn't go over 10 minutes after practicing a lot of times.
Okay, thanks guys. Nice job. We're gonna move on to group 9 now. And in group 9, the first presenter will be Wenhao Li, second will be Keha Tang, and third will be Qin Wang. The floor is yours. Who's going to be presenting? And guys, if y'all can, to turn on your camera while you present. You know, I think it's nice practice for you to present this way. So.
Hello, this is Wen. I'm gonna share the screen for my group members.
Okay, thanks, Wen.
So you mean I should turn on the video, right?
Yep.
Okay.
I mean, you may do that. You don't have to. It's good to see who's presenting, but if you don't feel like sharing it with us, that's fine.
要不你 mute 吧，你 mute。
行。
没关系，要说话。
什么？我 mute 吗？还是
We can hear you.
Are you ready?
Yeah, I'm ready. Good afternoon, everyone. We are group 9, and our project is predicting mortality for ICH patients with various machine learning models. Here is background information. ICH is the sudden leaking of a blood vessel over the surface of the brain. ICH can be life-threatening, and it happens in about 1 per 10,000 people per year. In the US, the incidence is about 0.32 per 10,000 years on average in South and Central America regions. Our task is to predict mortality for ICH patients in the provided test data set using machine learning models. Here's the data description. The data we use in project are from the EMR for ICH patients. There are 3 data sets: demographic variables, medication, and procedure. There's a total of 9411 calls from patients in the data set. The primary outcome is mortality, and its corresponding variable is size in the data set. The first 2 figures show in bar plots of gender and race with size. The first plot shows the distribution of weight among two dice categories. And we can say that Caucasian in green color and African American in pink have higher population. The second plot shows that there are more females in pink color than males in green color. The third figure shows that distribution of age in two groups. The plot shows that distribution of age is less skewed in the dice group, indicating that the older people have higher mortality rate. This flow chart generally shows the dice we have done for processing data. There are 3 training data sets and 3 test data sets in the raw data. We first combine the 3 training data sets by reshaping the medication and procedure from wide to long and creating column variables for each medication and procedure category. There are 4911 observations and 1952 variables in the training data set. And we further scale the data into chain with 80% and type 20% data size. We did the same processing for the type data set and to make it have similar structure model with the training data set. We added new column for the non-overlapping variables and coded them as 0. Linear branch of statistical and machine learning models that we tried, including logistic regression, lasso regression, PCR, PLS, random forest, Petboost, SVM, neural networks. We pick a few that we have pretty good performance to introduce today. We start with logistic regression model, but the performance is not good enough. As the data have a large number of variables, we proceed with lasso regression. The initial model was fed with GRMNet, and the data were automatically standardized. Training parameter lambda by CV the GRMNet. The predict function was applied on the type data. Principal component regression. Since there are 1952 variables in our dataset, and some variables are highly correlated, therefore we can do dimensional regression by using PCR. We build a PCR model with package PLS in R. Random forest modeling. Random forest is one of the most versatile machine learning algorithms widely used for classification problems. A default model was implied with package random forest in R. Training method is that initial training with random forest and foreground search with ranger package in R. Number of words in the forest is from 500 to 3,000. Number of words at each square was returned by using kernel RF. Minimum number of samples within the terminal nodes are from 1 to 10. Fraction of samples to train on from 0.5 to 0.8. The sample with replacement are between true and false. Support vector machine. We built SVM model with package E10 71 in R and with 2 kernels. Hyperparameters, of course, are from 0.1 to 1000. A gamma is from 0.01 to 4. We use 10 for customization. The next part is result.
All right, for the results for lasso regression, the best lambda corresponding to the minimum cross-validation MSE was found to be 0.0129, and it's showing the graph. And by applying GRMNet on the training data with the best lambda, the number of non-zero coefficients is 98. And this bar plot shows the non-zero coefficients on the x-axis, and the y-axis shows the corresponding variable names. The large positive coefficients was 2 procedure variables. They're not listed here, but they're circled in the graph. And for lasso regression, the overall accuracy on our test data is 0.8271, and this is pretty good. For PCR, we chose 198 components, and we have the highest prediction accuracy calculated from the confusion matrix below is 0.8294. For the random forest, the best model from random forest is with number of trees set to be 15,000, and the number of variables at each slit is 44, which is our default value, and the node size is 1, sample fraction is 0.63, and the replacement is set to be true. And with this best model, we had our lowest out-of-bag error is 0.179, and the prediction accuracy is 0.8198. And this plot shows the variable importance measurement from the top 10 important variables. And you can see that age in years is an important one, and some medication and procedure variables listed here. And this is very consistent with the lasso regression result. The result for support vector machine has our best model is with radial kernel, and the cost function equal to 2, and it has 2069 support vectors. We evaluated with tenfold cross-validation, and the prediction accuracy in the split test set is 0.8454. And this slide shows the more results from SVM model. The left graph shows the performance of SVM with different hyperparameters, cost and gamma. And the right graph shows the ROC curve for the final model we chose. Discussion.
Chin?
Are you going to present our discussion? Can I go ahead? This is one.
Yes, go ahead.
Chin, are you not there?
Yeah,
Chin?
I'm here. Can you hear me?
Yeah, we can hear you.
Okay. Discussion. X prediction is our primary goal. The model with the highest prediction accuracy on the split test set was chosen as our final model, SVM model with accuracy 0.8454. The drawback of PCR is that the response variable is not taken into consideration when deciding which principal component to drop. Random forest is computationally expensive and needs lots of memory. It is not good at generalizing on completely new data. Lasso, when the least squares estimates have excessively high variance, the lasso solution can yield a reduction in variance at the expense of a small increase in bias, and consequently can generate more accurate predictions. The lasso performs variable selection and hence results in models that are easier to interpret. Simple. Lasso is simple but not flexible. SVM is computationally expensive, and choose appropriate parameters is the key. In the SVM algorithm, several key parameters need to be set correctly to achieve best classification. Thus might have issues of overfitting. And the limitations and data structures are different in training and test set, and this may affect the performance of a model on test set. In data processing, non-overlapped variables are coded as 0. There may be better ways to handle this issue, but we went with the easy way. We could try a broader range of parameters. Parameter tuning may improve the model. That's all. A reference. Thank you for your attention. Any questions?
Any questions from students?
Hi, I have a question. When you say that
variables were coded to 0, does that mean that you have them missing, or just change the values to 0 in comparison to other variables that have values greater than 0? Because I feel like that would affect your results.
Yeah, thank you for the results. So we actually compared the categories in the training data and the test data, and there are some variables that were in the training data but not in the test data. And so we added those columns and coded them as 0. Did that answer your question?
So you used a new variable and set it to 0 if it wasn't in both of the columns.
Right. Mm-hmm. No problem.
So I have a question. So you were just saying there are like some variables that you have in your training that you kept in your training, or did you remove from your training, right? So you removed some variables from your training data?
We didn't. I think we try to keep all the categories the way as they are and use their count.
So there shouldn't be, like if you remove a variable from your training data, so you think about it, if you train an algorithm on variable x1, x2, and x3, and then you make a prediction, you have to have in your testing set the same variables, and whatever pre-processing that you did for your training data, you need to reapply this to your testing data set. Otherwise, it will be what you're doing will not be accurate.
Yeah, exactly. So I think that's what we did actually, and that's why we try to add those variables in the test set and add them and put them as 0. Just to make it have a similar structure as the training data to apply the model we just built. Does that make sense?
But your testing set is part of the whole data set that you give it to you, right? So from the beginning,
So yeah, that test set, I mean that real test set that we use which we don't have a real mortality result.
Okay. So the one that we gave you.
Exactly.
Okay.
Yeah, we kind of manipulate that data to make it has the similar structure.
Okay.
So you're saying that you took the union of all the variables from the training and test set?
Yes.
Whereas the previous group took the intersection of the variables?
No, actually, for the training data set, we didn't manipulate the training data set. We only changed the data structure for the real test data set. So we didn't delete any variables from the training data set.
Yeah, that being said, we use the union of both variables in both data sets.
That's right. Right, so you took the union, you just added variables that were in one set but not in the other. Yeah. Okay. Other questions from students? So Tara asked, does that work? But did it work?
No, I guess I mean, like, how can you predict on the test if technically the variable wasn't there and you made it up?
Yeah, actually, we also mentioned it in our discussion session. This is one of a simple way to dealing with this kind of questions in non-overlapped variables. But in literature, there might be more ways, maybe more complex ways dealing with that. But this is one of the most a chosen one, and many data scientists do predictions using this, like union of variables.
Other questions? So with respect to the union of the variables, certainly both approaches can be taken. Keep in mind that like if you add, here's a variable in your test set but not in your training set, and you add in your training set another variable that has just a bunch of zeros, that's not adding any information for your training model, right? So that variable will never be, like, if you were to do variable selection, that variable will never be chosen because it's just, there's no variation, it's just zeros.
Yes.
Right.
Right. If, on the other hand, like if you have a variable that's in your training but not in your test set, and then and you find that that variable is important in your training set, and you can assume that in your test set the reason it wasn't there is just because no one happened to get that medication, then you could use it that way. That would probably give you more information that way.
Yeah, that's a good point. Sorry for the, yeah, actually by saying union, I mean we included all the variables that is in the training data set. And if the variables are not in the test data set, we added those variables. But if there's some variables that the test data set has, but training data set doesn't have, we didn't add them in the building the model. We just deleted them in a test data set.
Okay.
Because that doesn't bring like any information.
Okay. So Nupur put a comment. Hongwei, if you're on it, you can check that. So what was your final model that you chose? I saw several models at the very end. Which one was the final model?
We chose a model according to our prediction accuracy, and the SVM model was chosen.
SVM.
Yeah.
All right. Let's move to the last group. We don't have enough time for more questions. So who's the last group?
Group 2. So the first presenter will be Fan Shen. Number 2 will be Tanya. Number 3, Sanji.
Okay.
Nice job, Group 9.
Thank
Good
you.
job, yeah.
Thank you.
Yes, good job. Very good job.
Can everyone hear me?
Yes.
Yes. Okay. Go ahead, guys. Ben, are you there?
Yes, I'm here.
Okay, go ahead.
Is this sharing good? Can you see the PPT?
We can see the slides, yes.
Okay.
Yeah, please go ahead.
I cannot move. I cannot move the pages. Yeah, I don't know why.
You have to change which screen you're sharing,
Um,
and then you'll have to actually click on the arrows to change the slide, because right now you're showing us your notes page.
Fan, I believe Kush is presenting.
what? Kusher.
For us.
Sorry. I cannot share the document. So Kush, could you please help us to share the document? Thank you.
Chris, you can change the slides, right?
Could you can you move the pages? Can you control the slides?
Yeah, it looks like it.
Okay, thank you. Okay, so I'm presenting our project, which is to predict mortality in SIAH. SIAH is short for the bench noise.
Ben, can you give me 1 second?
Sure.
I think we need to make a decision here because it's already 3:45. So our WebEx will probably cut off unless we get it extended, but some students may have to leave. So
okay.
I like to probably we can probably start the presentation and finish next time, or we can just start at the beginning on Wednesday, which I think should be okay. Ashraf, do you have a preference?
I think next time, yeah, if we can move it, because I understand some students may have some other classes. So maybe if this group can start next time, and it will be better, I guess.
Okay, well, let's just do that then. Group 2, so y'all start, and let's try to start right on time on Wednesday, so I have everything ready for you.
Okay. Okay, sure.
And yeah, I don't think the quizzes are timed, Anna, and so you can still complete that later. Are there, in the last few minutes, are there any questions about the project or any other comments? Okay, and then Fan and Group 2, if y'all can work out your issues with the presentation, because it looked like it was still on the slide with the notes as being displayed over WebEx. So if y'all can practice between yourselves to make sure that you're presenting the right screen.
Okay.
Yes, so Anna is asking, what if we already opened the quiz to score them? There is no...
I already mentioned that it's not timed.
Oh, yeah, you already mentioned that. So it's not timed, Anna.
But if we close it, can we reopen it later? Because I don't know if it, I think so.
If you open it, it will probably take you 1 or 2 minutes to finish it. So why do you want to go back to it again?
No, if somebody opened the one for the presentation that was about to happen, will they be able to reopen it next time?
I think you can still do that. If you have any issues, you can, send us an email or to the TAs. We can, figure it out.
And yes, the final is still scheduled.
Yes, we will have a final exam review on, let me see, when? Next week. We should have a final exam review on the 22nd, April 22nd. All right, any other questions?
All right.
All right.
Thanks, everyone. Bye.
So stay safe, everybody. See you next time.